Dear colleagues, let me present a report on the topic, the method of tactile sensor signals processing in bionic hand prosthesis. The possibility of implementing the function of tactile sensations in a bionic prosthesis is based on solving two main problems. Teach the prosthesis to perceive external objects and form on this basis certain informative signals by which those objects could be distinguished. Teach the user to correctly perceive those informative signals. Regarding the solution of the first problem, it involves the use of specialized sensors. In particular, the design of resistive, capacitive, piezo, and optical sensors are known. This research presents the results of the development of a simple system for providing tactile sensations. Piezoelectric transducers are used as tactile sensors. As actuators for vibrotactile stimulation, it is also proposed to use piezoelectric transducers to create vibrations that will be perceived by the mechanoreceptors of the patient's stump skin surface. For the correct and reliable operation of such a system, it is necessary to develop a method for processing tactile sensor signals and forming control signals for the corresponding actuators with minimal time delays. In this research, as the base model of a prosthesis was used 3D printed and fully assembled kinetic hand prosthesis. In this prosthesis, special inserts made of elastomeric material are placed in the distal flanks of the fingers for better gripping and holding of various objects. They are white elements at the ends of the fingers. As sensors, they used small-sized disc low-frequency piezoelectric transducers of sound emitters. One of those transducers was placed in the elastomeric thumb insert. To record signals for such a sensor, the ADC of the laptop sound card and the corresponding microphone input were used. The Adobe Audition program was used for the actual recording. During the recording, slight touches were made to the elastomeric thumb insert with the sensor. In the next stage, a group of signals from the sensor were registered during slight touches, stroking, tapping, and pressing on a prosthetic elastomeric insert. Those signals were loaded into the MATLAB environment for subsequent analysis. Furthermore, it is necessary to process the received signals to highlight in their structure informative things about the peculiarities of impact on the elastomeric insert. Further, those signals will be used to form actuator control signals. Processing methods should ensure signal processing in real time with minimal delays. It was made the assumption that the main information about the type of impact on the elastomeric insert will be contained in the structure of the envelope component of a sensor signal. Therefore, it was proposed to isolate the envelope component of such a signal and use it to form actuator control signals. To process the signal, a sliding window was formed, which was translated into a time along the recorded signal and within which the search of the maximum value was performed. Figure 6 shows the form of a sample from the signal and the corresponding obtained graph of the change in the maximum value within the sliding window. Figure 7 shows the maximum value signal. Figure 8 shows the sensor output signal with the superimposed maximum value signal. As noted earlier, it is proposed to use a low-frequency piezoelectric transducers as actuators, which will create mechanical vibrations under the action of electrical control signals. Thus, for this purpose, it is proposed to form an amplitude-modulated signal, the carrier frequency of which will correspond to the resonant frequency of the transducer, and the envelope component will contain information about the effects on tactile sensors. That is, it will be the maximum value signal, the obtaining of which was described above. The resulting amplitude-modulated signal, after amplification, is fed to the corresponding actuator. To reduce the level of energy consumption, it is proposed to additionally form a threshold signal from the sensor output signal, which will start the process of generation the carrier component of the actuator control signal. Figure 9 shows the appearance of the sensor output signal, the maximum value signal, and the threshold signal. Also, in the MATLAB environment, an amplitude-modulated signal with a carrier frequency of 3 kHz was formed. The appearance of this signal is shown in Figure 10. Accordingly, it is this signal that will be fed to the actuator after amplification. In this case, the degree of mechanical deformation of the actuator will correspond to the parameters of the envelope component of the sensor signal, which will correspond to the dynamics of the latter perception of external loads when touching or grasping objects. In the future, using such a system of tactile sensations, prosthesis users will be able to learn to feel the grasping of objects and differentiate their own sensations. The proposed design is simple and reliable and will have a negligible impact on the costs of the prosthesis, despite a significant expansion of its functionality. Thank you for your attention.